Cats are known for their incredible balance, agility, and sharp reflexes. Their keen eyesight and acute sense of balance allow them to move effortlessly in various environments. But what happens when these agile creatures are exposed to the challenges of zero gravity? Understanding how a cat's body reacts to weightlessness can provide valuable insights into the neurological and physiological changes experienced in space. During the early years of space exploration, various animals were sent into orbit to help scientists understand how microgravity impacts biological systems. Unlike other species such as dogs and monkeys, cats were not frequently used in space missions. However, in 1963, France sent the first and only known feline astronaut, a cat named Felicette, aboard a suborbital flight. Felicette, a stray cat from the streets of Paris, was selected for the mission by French scientists. She was trained for space conditions by being placed in small capsules, exposed to loud noises, and subjected to G-forces in a centrifuge. On October 18, 1963, she became the first cat to be launched into space on a suborbital flight aboard the Veronique AG-1 rocket. The mission aimed to study how microgravity affects a mammal's nervous system, particularly focusing on balance and coordination. During the brief flight, electrodes implanted in her brain recorded neural activity. As the rocket ascended to 157 kilometers, the weightlessness affected her vestibular system, which is responsible for balance and spatial orientation. Unlike other animals, cats rely heavily on their inner ear system to detect gravity and position their bodies. One of the most fascinating findings from feline spaceflight experiments involved the cat's ability to right itself mid-air. On Earth, cats use a righting reflex to twist their bodies and land on their feet. This reflex relies on signals from the inner ear's vestibular system. In microgravity, however, this response is significantly altered. Instead of performing their signature aerial maneuvers, cats sent into space struggled to determine their position. Video footage from the 1963 mission showed that the cat flailed and exhibited uncontrolled movements during the weightless phase. This suggested that microgravity disoriented the cat's natural ability to maintain balance. Scientists speculated that the semicircular canals, fluid-filled structures in a cat's inner ear responsible for detecting orientation, failed to send clear signals in the absence of gravity. Without gravity's pull, the sensory information that cats rely on to adjust their posture is lost. Unlike on Earth, where a cat's righting reflex helps it quickly rotate its body mid-air, space conditions cause disorientation, making it harder for the animal to determine which way is up or down. Studies on cats in microgravity have also examined changes in their muscle tone and bone density. In space, the lack of gravity results in muscle atrophy due to reduced use. In microgravity, cats do not need to use their limbs to support their weight, which leads to a decrease in muscle mass. Their bones also weaken over time due to decreased mechanical stress. Research suggests that cats, like other mammals, experience a loss of bone density in prolonged spaceflight. The effects on their bones have implications for human space travel, as astronauts face similar risks of bone demineralization. When astronauts return to Earth, they require extensive rehabilitation to regain their muscle mass and bone strength. If cats were to spend extended periods in space, they would likely face similar challenges upon return. The effects of microgravity on feline behavior are also a subject of interest. On Earth, cats use their whiskers and inner ear balance system to navigate their environment. In zero gravity, they may struggle with balance and movement. Observations from the French space mission with the cat Felicette showed signs of disorientation in microgravity. Unlike humans, cats rely heavily on their vestibular system for spatial orientation. The absence of gravity can disrupt their natural sense of balance, making it difficult for them to move in a coordinated manner. When floating in microgravity, cats appear confused and make unusual, exaggerated movements. Scientists believe this is because their inner ears, which help them determine up from down, are no longer providing consistent signals. Upon returning to Earth, cats experience a temporary adjustment period as their bodies readjust to gravity. The long-term effects of microgravity exposure on a cat's motor coordination remain an open question. Cats are highly adaptable animals, but their dependency on gravity may limit their ability to function effectively in prolonged space environments. Research on animal adaptation to space is crucial in planning future extraterrestrial colonies. Microgravity also influences the way animals perceive their environment. For cats, whose survival depends on quick reflexes and sharp orientation, the lack of gravity can be disorienting. Their brains receive confusing signals from their vestibular system, which can result in uncoordinated body movements. Space agencies have studied these effects to better understand how the human inner ear adapts to microgravity. Motion sickness in space is a common phenomenon that affects both animals and astronauts. Just like humans, cats can experience space adaptation syndrome, leading to nausea and dizziness. Research suggests that some animals adapt quickly, while others struggle with long-term disorientation. Studies on spaceflight effects have also provided critical data on the impact of microgravity on sensory processing. Understanding how microgravity affects vision and coordination is vital for designing future space habitats for both humans and potential animal companions. The role of animals in space exploration raises ethical considerations about their well-being. Scientists and animal rights activists have debated whether sending animals to space is ethically justifiable. Many argue that while these experiments have led to groundbreaking discoveries, technological advancements may soon render them unnecessary. Alternatives such as microgravity simulations and organ-on-a-chip technologies may replace the need for live animal testing. NASA and other space agencies are actively investing in robotic models and advanced simulations to reduce reliance on animal testing. Nevertheless, for decades, animals have played a crucial role in shaping our understanding of how life adapts beyond Earth. The lessons learned from Feline and other animal space missions will continue to guide our pursuit of human space colonization. Understanding how animals adapt to microgravity is essential for long-duration missions, including travel to Mars. The future of space exploration may rely on bioengineered organisms adapted to survive in space conditions. As scientists develop artificial gravity technologies, the effects of microgravity on animals will become a key factor in spacecraft design. The mystery of how feline eyes and bodies respond to weightlessness is only beginning to be unraveled. With each new space mission, scientists uncover more about the resilience of life beyond Earth. The insights gained from studying animal adaptations to zero gravity will help shape the future of space travel. As humanity prepares for interplanetary colonization, research on how living organisms function in microgravity remains critical. Understanding how feline eyes react to zero gravity is a fascinating step in uncovering the mysteries of space biology. The story of animals in space is one of curiosity, sacrifice, and discovery, paving the way for future generations to explore the cosmos.